Welcome to This Explainer. If you've ever sat on a train just absolutely flying through the countryside or rumbling deep underground, you've probably wondered how thousands of tons of metal avoids colliding with all the other trains sharing those exact same tracks. Well, today we're bringing an invisible, highly structured safety net to light. We're going to break down the technical principles of railway control and communications. It's an absolutely fascinating look at the anatomy of a single train movement and the brilliant, fail-safe systems that are designed to protect it. Okay, so let's dive right in by defining our core signaling philosophy. Really, everything we're about to discuss is built on a massive, delicate mathematical balancing act. On one hand, you've got absolute safety, literally minimizing the risk of human error to zero. But on the other hand, we need maximum efficiency. We need to run as many trains as physically possible on a given stretch of track just to keep passengers and freight actually moving. So every single piece of railway signaling equipment exists to serve these two competing goals, safety and efficiency. Think of this as our syllabus for today. We're going to dissect the complete life cycle of a train movement across 5 systematic principles. Number 1, safe route setting. 2, movement authorization. 3, route maintenance. 4, train supervision. And finally, number 5, route release. All right, kicking things off with step 1, safe route setting. Establishing a secure path before motion even begins. So the crucial point here is a concept called interlocking. Think of the interlocking system as a strict, totally uncompromising gatekeeper. Before a driver is ever given a green light, the system runs through a mandatory checklist. First up, it makes sure all points or switches on the tracks are locked in the exact correct position. Next, it proves through train detection systems that the physical track section ahead is completely clear of any other trains. And finally, it checks its own memory to guarantee no directly opposing routes or conflicting train movements have already been authorized. These systems are designed to meet what's called Safety Integrity Level 4. Basically, that means the likelihood of an unsafe failure is incredibly small. Moving right along to step 2, movement authorization, granting formal permission to proceed. Now, this brilliantly illustrates how traditional absolute block systems visually provide that authority. Because, let's face it, trains are incredibly heavy and they run on steel wheels, so they literally cannot stop within the distance a driver can see. I mean, a heavy freight train, that can take over a mile just to come to a complete halt. So to manage this massive braking distance, lines are divided up into blocks, and only one train is permitted in a block at any given time. The multiple aspect signaling you're seeing here spaces trains out by a strict braking distance. If a block ahead is occupied, the signals behind it will display restrictive colors, like a single or double yellow. That gives the following train plenty of time and distance to hit the brakes way before ever reaching a red stop signal. What's really fascinating here is this stark contrast in how we actually communicate those limits to the driver. Globally, we basically use 2 main philosophies. Route signaling tells the driver exactly where they're going, maybe by lighting up a junction indicator, but it relies heavily on the driver's own intricate route knowledge to know that, say, taking a diverging track means they need to slow down to 40 miles per hour. On the flip side, we have speed signaling. This explicitly tells the driver the exact target speed required for the route ahead. You don't necessarily even need to know where you're going. You just have to obey the precise speed code that's displayed. That brings us to step 3, route maintenance, holding the infrastructure secure. Unlike a car on a highway, a train obviously can't just swerve or steer to avoid an obstacle. It is entirely at the mercy of the rails beneath it. So the system uses what we call route locking. Once a train enters its authorized path, the interlocking system physically locks the points and switches ahead of it. Even if an operator in a control center makes a massive mistake and tries to route another train across that path, the system literally will not allow the track to physically shift while our train is moving through its reserved space. It's locked in. But wait, what happens in a sudden emergency? Like, what if a signal suddenly drops to red while a massive train is barreling right toward it? Well, this is exactly where failsafes like approach locking come into play. If an authority is suddenly rescinded, the system doesn't just instantly unlock the track. If a train is already so close to that red signal that it physically can't stop in time, the approach locking steps in and maintains the reservation. It holds that track totally secure to protect the braking train from derailing on moving points. It ensures a safe outcome, even during a chaotic system disruption. Next up is step 4, train supervision, enforcing the limits of authority. Check out how supervision actually evolves to improve that efficiency we talked about at the very beginning. The top image shows the traditional fixed block system we just discussed, those static sections of track. But the bottom image, that shows a moving block system. and this is a real game changer. Here, the system constantly tracks the exact location and speed of the trains in real time. The safe zone, or block, is no longer just a fixed piece of track. It dynamically hugs the train. So, if the train slows down, its required braking distance shrinks, which means the train behind it can safely pull up much closer. It brilliantly maximizes the capacity of the railway without sacrificing a single ounce of safety. And to actually enforce all of this, we use automatic train protection, or ATP. The ATP system continuously calculates a safe speed profile based on the train's braking ability and the distance to the train ahead. It's constantly comparing the train's actual speed to this maximum safe speed. So if a driver gets distracted and goes a bit too fast, or approaches a red signal too quickly, the system sounds an alarm. And if the driver ignores it, the ATP intervenes and automatically slams on the brakes to bring the whole thing to a safe halt. It completely mitigates the risk of a driver passing a signal at danger. Finally, we reach step 5, route release, freeing the track for the next movement. To maintain that all-important efficiency, the interlocking system does not wait around. I mean, the literal millisecond the rear axle of a train clears a protected junction or a section of track, the train detection sensors report it as empty. The interlocking system then immediately releases the route locking directly behind the train. This rolling release ensures that the track becomes instantly available to authorize the next train movement, keeping heavy traffic flowing smoothly through really complex junctions. So to quickly summarize our masterclass for today, every single safe train movement, whether we're talking about a high-speed intercity express or just your local underground metro, relies on this exact 5-step sequential philosophy. First, you set a safe and clear route. Second, you authorize the train to move. Third, you rigorously maintain and lock that route while the train occupies it. Fourth, you actively supervise the train's speed and position. And fifth, you efficiently release the route the absolute moment it's safely cleared. I want to leave you all with this final thought. The next time you're on a train and it mysteriously slows down or pauses just outside a station, don't just sigh in frustration. Think about everything we've learned today. What you're actually experiencing in that moment is the invisible hand of the interlocking and supervision systems hard at work. It's reading the track ahead, checking braking curves, maintaining a protective buffer, and actively ensuring that your path is absolutely, undeniably safe. It's a massive, brilliant engineering safety net working exactly as designed. Thanks so much for joining me for this explainer, and definitely keep your eyes peeled the next time you ride the rails.